Hello. Welcome back to another weekly theory session. Today, Ellen is here, and she's going to tell us about estimating approximate incentive compatibility. So thank you.
Thank you. Okay, thanks. So this work is joint with Nina Balkin and Thomas Santholm, and it was published this summer in the Conference on Economics and Computation, or EC. So this talk is about auctions. So what is an auction? In an auction, there's one or more items for sale. Agents report their values for those items to an auctioneer. And the auction defines what the agents get, so how the items are allocated, and how much the agents pay. This talk is going to be primarily concerned with the notion of utility. And this is how much the agents value what they get minus the price that they paid. And it's really important when you're thinking about an auction to think about how the agents are going to be incentivized to interact with this auction. And in particular, an auction might be defined such that agents can maximize their utility by bidding strategically. So when they report their values to the auctioneer, they might be lying about what their true values for the items for sale are. So this brings me to the notion of incentive compatibility, which is a fundamental concept in mechanism design or auction design. And an auction is incentive compatible at a high level if the buyers will maximize their utilities by bidding truthfully for the items for sale. And incentive compatible mechanisms are really nice because we can just so easily reason about how the agents are going to behave when faced with this auction. But nonetheless, many real-world mechanisms are not incentive compatible. So I'm going to give a few examples of non-incentive compatible mechanisms. The first is the first price auction. So let's say we're in a specific scenario where there's one item for sale, you're a bidder, and there are two other bidders. You don't know the other bidder's values, but let's say you happen to know that those values are drawn IID from the uniform distribution between 0 and 1, just to give a concrete example. Here's what happens in the first price auction. The buyers submit sealed bids to the auctioneer. So this means that the auctioneer gets to see each bidder's bid, but each bidder doesn't get to see the other bidder's bids. So you submit these bids to the auctioneer. The highest bidder wins, and that bidder pays their bid, so they pay the highest bid. Okay, so the question is, how should you bid to maximize your expected utility? And the expectation is over the draw of the other bidder's values. So expected utility. Remember, utility is your value for the items that you got minus the price that you paid. So if you don't win the auction, your utility is going to be 0. You don't get any items and you don't pay anything. Otherwise, if you do win, your utility is your value minus the price you paid, which is your own bid. So the question is, in this setup, how should you bid in order to maximize your utility? You can also assume your value is bounded between 0 and 1. And we can also assume, for simplicity, that the other agents will bid truthfully. Okay. So I'm going to tell you what you should do. So again, we're in this scenario where there are two other bidders whose values are drawn IID from the uniform distribution between 0 and 1. So the expected utility of a bid V tilde is going to be in expectation over the other two bidders' bids. 1, if your bid is greater than their bids, times your value minus the price you paid, which is your own bid. And otherwise, if your bid was not higher than the other guy's bids, your utility is going to be 0. And since we're in this nice scenario, where the other bidder's bids are uniform, we can work out that your expected utility of a bid V tilde is just this expression here, V minus V tilde times V tilde squared, where V is your own distribution, or is your own value. Okay, and it's really easy to work out that this expression is maximized when your bid, V tilde, is 2/3 of your value. So in general, the first price auction incentivizes bidders to shade their bids. In more general scenarios than this, for different distributions, it generally holds true that the first price auction will incentivize the bidders to bid something that's slightly lower than their true value.
Even in the worst case it holds? Or if you've done any prior?
And maybe not for the worst case prior, but in general, this is true. Yeah.
So when you're defining incentive compatibility, are you assuming like there's no cooperation going on?
Yeah, I'm assuming the agents are kind of, removed from each other.
And also that we only care that there is a stable position if everyone is truthful, not that there aren't other.
Yeah, we're just thinking about this specific type of incentive compatibility, which I'll make really way more formal later on, where other bidders are truthful. What is like my strategy? Okay, so we saw the first price auction is not incentive compatible, and first price auction is kind of like the most basic auction you can think of, and we see it around us in the real world all the time. There are also non-incentive compatible mechanisms that are used in the real world, such as the discriminatory auction, which is basically a multi-unit variant of the first price auction. So there's not just one item for sale, but there are multiple identical goods for sale. This is not incentive compatible, but it's been used to sell treasury bills in the United States for decades. And it's also used to sell electricity in the United Kingdom. Another example of a non-incentive compatible mechanism is the generalized second price auction. This is used in sponsored search. So when you make a search on a company like Google, you'll see oftentimes these ads interspersed with your search results. And the way this happens is as soon as you make that search, there's an instantaneous auction that occurs for the opportunity to show you these ads. And this, the auction that's most commonly used, or variants of it, is called the generalized second price auction. And it's not incentive compatible.
So what's wrong with, it seems like you're just trying to maximize the seller's position, right, and not the buyer. It's good for buyers. I'm a buyer. I don't sell too much. So why would I want to play, if I have my choice of two auctions, wouldn't I want to play this kind of auction?
A non-incentive compatible one? Yeah, so I guess it does depend on how much revenue you think you're going to get as a seller. But the nice thing about an incentive compatible mechanism is you don't have to reason about like, are the agents going to be playing in one national equilibrium versus another? There's kind of a really obvious dominant strategy for them to use, which is just bid truthfully. So it's just easier to reason about what revenue you're actually going to get as a seller if you use an incentive compatible mechanism.
But I have to know the utility.
And as a buyer, it's easier to make your decision of what to bid because you don't have to, you can just say how much.
That's true.
My experience on eBay is since I have no idea what the utility is,
Oh, I see.
it doesn't matter, right? I mean, for me, second, I don't see why I would want to care. I would probably prefer to play the first, right? Or why?
So you're saying as a seller on eBay,
Yeah.
you have no idea.
As a buyer.
As a buyer.
I mean, I don't sell on eBay. I
Okay.
only buy.
So, and you don't know your own value, is what you're saying?
Yeah, I think that's a big assumption. I mean,
Yeah,
it's
yeah.
an assumption, and you admit that.
Yeah.
Okay.
It's an assumption you make, but it isn't necessarily the only way of proceeding. with this.
Definitely, yeah.
As Gary said, I agree, it's not, because of the value you have, it has to do with how much other people think it's worth.
Yeah.
Stuff like that, so it's.
Yeah, definitely. In economic or in this kind of computational economics, we do generally assume that the buyers know their own values, and this is maybe a strong assumption because how should I know really how much I value a TV? It depends on a lot of contextual things.
So in all these non-incentive auctions, are they not incentive compatible in the sense that people will always bid less, or are some of these incentivize people bidding more than their value?
Yeah, I think maybe, so I'm not sure, but I wouldn't be surprised if sometimes you want to bid more than your value. Yeah. Okay. So the last one I just want to mention is basically all multi-item, multi-bidder auctions or combinatorial auctions that are actually fielded in the real world are not incentive compatible. So one example of this is sourcing auctions, which Thomas had a startup for. And basically sourcing auctions are the way in which large companies like Procter & Gamble obtain the goods and services to run their operations. And these are not incentive compatible. So why aren't real-world mechanisms incentive compatible? There's a lot of different reasons for this, but I'll just name a couple. So first of all, kind of related to what we were talking about, it can be really computationally expensive for buyers to actually compute their values for the goods for sale. So for example, let's say there are M items for sale, then a buyer, to compute their own value, they might have to compute a vector of length 2 to the m, one value for every bundle for sale. So this just might not be computationally tractable. They might not be able to participate in the auction that's designed to be incentive compatible. Another example is that for whatever reason, non-incentive compatible mechanisms often have rules that are easier to explain. So for example, the first price auction is extremely easy to explain, and it's not incentive compatible. Sometimes, especially in these ad auction scenarios, when there are like auctions going on every millisecond, bids on one auction might be used to tune the auction parameters of future auctions. So an agent who knows that this tuning is going on might be incentivized to be strategic now in order to hopefully get more utility later. Auctions might leak the agent's private values in the form of their payment function or their allocation function, so agents might not want to actually expose those private values by bidding truthfully. And finally, agents are sometimes not risk neutral, so an auction that is incentive compatible for risk neutral agents may no longer be incentive compatible when the agents aren't risk neutral.
So when people don't bid into the last second, that's because even though they're trying to be incentive compatible, they're not? Because if you notice that all people, I don't know why, only bid in the last few milliseconds. Right, they have this special clock and they do all kinds of things. But you'd think that would be for incentive, because it's not incentive. Otherwise, according to you, since they all use the incentive compatible auction, people should just bid at the beginning of the week and just see if they win at the end of the week. Right?
So they don't have. So they're seeing what the current bid is. Maybe they don't want to push the bid up themselves. I'm not sure.
All I know is that most all auctions take place in the last few milliseconds.
I'm not sure. I'm guessing it's they don't want to push the bid up by bidding, or the highest bid up by bidding right now. They want to wait as long as possible so that the bids don't keep rising in response to their own bid. That would be my guess.
So I thought I thought you were supposed to bid your true value. Does it matter when you
So these are all the auctions I'm talking about are just sealed bids. So everybody just bids their bid, sends it to the auctioneer. Nobody else sees it. There's closed bids. Whereas it sounds like what you're talking about, it's not closed. You get to see how it evolves over time.
People might not want to give the information of their true bid, so they leave it to the last minute where nobody can react to their.
React quickly enough.
But their true bid is never shown.
Is it?
Only if you get beaten. If you're still the highest one, it doesn't show your maximum bid, right? It's a sealed bid, second price auction. But I guess you're allowed to keep putting new bids in all the time. I never do. I do buy it on eBay, but I never do the last minute thing. I just decide what I want to pay, and I just don't fool around.
But the other people bid.
The other people do. Yeah, I don't know.
I'd like to hear a little bit more about approximate incentive.
Okay, cool. So since most mechanisms are not incentive compatible, a long line of research has looked into approximate incentive compatibility. So I'm just going to describe it at a high level here, and then I'll describe it more mathematically in a couple slides. So an auction is gamma incentive compatible when for each bidder I, if everyone except bidder I is truthful, she can only increase her expected utility by an additive factor of gamma by bidding strategically. And this kind of flavor of approximate incentive compatibility has been studied pretty extensively in the literature. Okay, but I'll come back to this. I'll come back to this and show more mathematically what I mean by this. So our goal in this work is, given samples from the distribution over buyer's values, can we estimate this incentive compatibility approximation factor using those samples? So we want to estimate gamma just using samples. And this question is kind of complementary to a line of literature on revenue maximization via machine learning, or sample-based revenue maximization, where you get these samples from the distribution over buyer's values, and you want to tune auction parameters so as to maximize expected revenue. Right. So these are related in that both of us are sampling from this distribution over buyer's values. We don't know the distribution, we only get samples, but they're unrelated further than that. Mm-hmm.
When you say over agents' values, they're agents' true values?
Yeah, we get samples over from the distribution over the agent's true values. Okay, so now I'm going to make all of this a bit more formal by giving some background. So in general, we're going to be looking at settings where there are m items for sale and n buyers. Each buyer I has a value vi of b for every bundle of the m items. And we're going to use the notation, this vector vi, to denote this vector of length 2 to the m of bidder i's value for every bundle for sale, all to the m bundles. And we're going to make a standard assumption, which I've alluded to already, that the buyer's values are drawn from some distribution. So this vector, or this tuple of vectors, bidder 1's values up to bidder n's values, are drawn from some distribution D. And in this talk, we're going to assume that D is a product to distribution. So in particular, each bidder i's values are drawn from some distribution di. And this distribution D is the cross product of those n distributions. And I'm going to use the notation D minus I to denote the distribution over all buyer's values except bidder I. And I'm going to we relax this assumption in the paper, but I'm just going to make this assumption in this talk. Yeah. So a bidder's own values might be correlated, but bidder i's values are independent from bidder j's values. Okay, so an auction is defined by an allocation function and a payment function. X is the allocation function, P is the payment function. So what happens in an auction, and I'm just going to focus on the single item setting in this slide, because the multi-item setting, the notation gets a little too crazy, but you can probably imagine that it would generalize very easily to multi-item auctions. So in this setting, first, the auctioneer solicits a bid, vi tilde, from each bidder I. So this is just a number because there's just one item for sale. The allocation function x maps from the vector of bids to a 0, 1 vector, which is of length the number of bidders. And this defines who wins the item. So in particular, this resulting 0, 1 vector will have a 1 in the ith component if buyer I wins, and 0 in all other components. We also have the payment function, which maps again from the vector of bids, this time to a vector of length, the number of bidders, and it defines what the bidders pay. So the ith component of this vector is going to be how much bidder I has to pay. So like I've said already, the utility of agent I is their value for what they got minus the price that they paid. And now we can write this using this notation. So for bidder I, this xi of v tilde is going to be 1 if bidder I won. It's going to be 0 otherwise. So if they won, and if they won the item and this is 1, then their utility is going to be their value minus the price they paid. If they didn't win the item, then their value is going to just be, their utility is going to be negative of the price they paid. And throughout this talk, I'm just going to assume that this utility is bounded between -1, 1, and we can generalize this to bounded intervals -h, h, and the h would just appear linearly on our bounds. Okay, so now we can say a little more formally what incentive compatibility actually means. Auction is incentive compatible if for any bidder, in expectation over the other bidder's values, her utility is maximized by bidding truthfully, so long as all the other bidders also bid truthfully. So, okay, let's see what this means mathematically. The utility of agent I, I'm just going to denote it as this function, u of their true value vi, their reported value vi tilde, and the bids of the other agents, which is v tilde minus I. And right, we saw that we can write the utility this way, where this is the allocation indicator function times their bid minus the price they paid given those bids. Okay, so an auction is incentive compatible if for each bidder, I, any true value they might have and any bid they might report, in expectation over the other bidder's bids, their utility from a truthful bid, so here where their true value is vi, their reported value is vi, is at least the expected value of their utility from that strategic bid. So here they're bidding vi tilde. Okay. And if you've seen incentive compatibility before, you might recognize that this is the ex interim definition of incentive compatibility. If you haven't seen it before, then don't worry about it. Okay, so now we can really easily define what approximate incentive compatibility is. So an auction is gamma incentive compatible if for each bidder I, any true value vi they might have, any reported value vi tilde they might report, their expected utility from that truthful bid is at least the expected utility from their strategic bid minus gamma. And again, this kind of like flavor of approximate incentive compatibility has been studied pretty extensively in the past. Okay, any questions so far? Okay, so now I'm going to get to the new stuff in this talk, which is our estimate of approximate incentive compatibility. So our overriding goal is to estimate this incentive compatibility approximation factor gamma using samples from the distribution over agents' values. So here's what you might first try, which is to estimate the maximum utility agent I can gain by misreporting her type on average over samples from the other agent's valuation distribution. So each v minus I is like a valuation vector of the other agent's bids, and where we have n many of these samples from the distribution over agents' values. Okay, so just written mathematically here, I'm saying take the maximum over all agent I's values and reported values vi tilde of the average over the samples of their utility from a strategic bid minus their utility from the truthful bid. And if you get enough samples and you can compute this max value, then indeed this will converge to the approximation factor gamma. But the problem with this approach is that this expression, this average here, is non-convex, and there are many discontinuities, as I'm going to illustrate in a few slides. So actually computing this maximum value, there may not be a finite time procedure.
I should have asked this earlier, probably.
Sure.
Are there any assumptions over what the value function looks like? Like, for example, a value for a group of items that should be at least, or most like the value of each individual item and number.
So we're going to assume that their value for the empty set is 0. And yeah, I guess we probably would need to assume that this valuation function is monotone. But I can't think of anywhere we actually use that fact. So it's possibly we don't need it. Okay, right. So we can't do exactly this technique, so we're going to have to do something a little different. So here's our estimate that we actually analyze in this paper. So again, it's a maximum agent I can gain by misreporting our value on average over the samples. so long as our true and reported values are from some uniform grid discretizing the type space. So I am going to assume that this type space is like bounded. Maybe it's like the interval 0, 1 or something like that. So here's an illustration where we'd have the bid along the y-axis, the value along the x-axis, and we have some like uniform grid of this type space. And now, okay, now I can just rewrite our estimate gamma hat to be the maximum over any value and reported value in this uniform grid of the average difference between utility of reported value, utility of strategic bid, and utility of true bid. So that's our estimate. And there's kind of an obvious challenge, which is that we might miss pairs of true and reported values with large utility gains, but they don't happen to lie in our grid. Like maybe there's some strange spike that happens outside of our grid. So we're going to have to analyze or give conditions under which this won't happen. So in particular, our overall goal is going to be to estimate the difference between the true approximate incentive compatibility factor gamma and our estimate gamma hat. Okay, so I want to just illustrate what is the key challenge here. And it's that utility functions are volatile. And this is even evident when we look at this really simple auction class, the first price auction, where the highest bidder wins and then they pay their bid, the highest bid. And we can think of what the utility function looks like in this example. So here, I've got their bid, vi tilde, along the x-axis, and I'm plotting their utility for a fixed value vi and fixed values of the other bidders, v minus I. And let's say that the maximum competing bid, or the L infinity norm of v minus I, falls at this value. If the bidder's bid is smaller than this maximum competing bid, then they're not going to win the item, and they're not going to pay anything, so their utility is just going to be 0. Otherwise, once their bid grows larger than that max competing value, their utility is going to be their value minus their bid. Right? So it's just a line where like the y-axis or the y-intercept of this line would be their value, and it's just decreasing linearly with their bid. And this kind of these jump discontinuities are all the more apparent when we're averaging over samples. So here I have like maybe 4 different samples, and I've got the max competing bid from each of those samples, and I'm just averaging the function from the previous slide here over those 4 samples. So you can imagine that if you had a coarse discretization, which was just like this point, this point, this point, and you were trying to say, if I restrict the bidder's bid to just be one of these blue points in my discretization in this grid, what would utility be? Well, you'd mistakenly think that their utility is just 0, no matter what their bid is. So you totally miss out on this interesting part of the utility function. Yep.
I'm not sure I really understand the interaction between like the sampling aspect and the algorithmic aspect. Like if you, let's say you know all the values, does it become easy, or that's still a challenging problem that you want to solve?
What do you mean by know all the values?
Well, I mean, if they're specified, the distributions, I mean.
If you know the distribution over agents' values. Yeah, so there's been work that looked at, given a like specific distribution, what is the approximate incentive compatibility factor? So then we want to know, what if you don't know the distribution, but just get samples from this distribution? So I think it does get easier if you actually know the distribution over agents' values. Okay. Should I just move on? Okay. So the question is, when is this distribution nice enough that we can figure out that we can estimate that gamma just using this uniform grid? And to answer this question, we're going to rely on a notion called dispersion, which I'm going to define now. So functions f1 up through fn, let's say they map from Rd to R, are wk dispersed if every W ball in the domain contains discontinuities of at most k functions. And this was introduced by me and Nina and Travis Stick in a very different context. So just to give an illustration of kind of what intuitively dispersion means, let's imagine we plot the sum of these functions f1 up through fn. If for some interval, there are a lot of discontinuities in that interval, then these functions are not dispersed. Whereas if for every interval, not too many discontinuities fall within that interval, then they are dispersed. So that's dispersion at a high level.
So it's still dispersed even if there are a lot of discontinuities, but all those discontinuities are from a single function?
Yeah. Yep.
Wait, sorry, why are you plotting the sum? Like, can't there be lots of discontinuities, but the sum is like continuous-ish? To make the picture.
It's just to make the picture kind of simpler. Yeah. Okay. So now let's think about what would dispersion look like in the context of these utility functions in a way that we can actually use. So I'm going to say that samples v1 up through vn, where v minus I is the set of Bayer's values for all bidders except bidder I. So these are n samples from the distribution over agent's values minus bidder I. These samples induce L Lipschitz WK dispersion if for any true value vi, if you look at these functions that measure utility as a function of the bid vi tilde over all n many samples, so we've got n functions here. If these functions are piecewise L Lipschitz and WK dispersed, and let me just actually draw a picture of that. So here again, we've got that picture from like 5 slides ago, where we've got the bid along the x-axis, and we've got average utility on the y-axis. And we saw this case where all the bids of the other agents were really concentrated in this interval. And so this set of functions, and many functions, are not dispersed. Whereas you could imagine if the maximum competing bids of the other agents were more just spread out, then we would have a more like dispersed set of functions.
You said the maximum bids, but it looks like you're actually talking about the maximum true value.
Yeah, I'm assuming the other agents are bidding truthfully.
Okay.
Yeah. Okay, and just to illustrate why dispersion is good, like we saw before, if we use, say, these 3 points as our grid, then we would think that, like, no matter the bid, the agent's value is 0. Whereas if we use this same grid on this more dispersed set of functions, we do get a pretty good idea of the maximum value of this function by just looking at the points in the grid. Okay, and just symmetrically for like symmetric definition for like the similar set of functions. So also for any bid vi tilde, the functions that measure utility as a function of the value are also L Lipschitz and WK dispersed. So these are just like 2 symmetric definitions for both, where you fix the value, look at the functions, or fix the bid and look at the functions. And this definition is kind of a mouthful, but we show that under natural assumptions, WK dispersion holds for good values of W and K. And I'm just going to describe what I mean by good values of W and K in a minute. Okay, so here are our guarantees that we give. So I just want, now that we've talked about dispersion a lot, I just want to remind you what our estimate was, this gamma hat. So it's the maximum utility that agent I can gain by misreporting her value on average over those samples, so long as her true and reported values are from the uniform grid G. And just written here, maximizing over vi tilde in this grid of the average difference between the utility of strategic bid and truthful bid. Okay, so here's the theorem that we prove. If for each bidder I, these samples do induce L Lipschitz WK dispersion, then we can use the W grid as our finite subset that we search over. And our estimation error is going to be with high probability. The difference between gamma hat and gamma is going to be LW plus K over N plus square root of D over N, where L is the Lipschitz parameter, W and K are the dispersion parameters, N is the number of samples, and D is like a standard machine learning measure of intrinsic utility or intrinsic complexity that I'm not going to get into here, but it's basically like VC dimension or pseudo dimension if you've seen those before. If you've seen those before, then the square root of D over N will look really familiar. So when is this actually a good bound? Ideally, this would go to 0 as the number of samples grows. So when W is basically 1 over the square root of the number of samples, and K is basically the square root of the number of samples, then our estimation error is going to go to 0 as the number of samples grows. And we prove that these W and K parameter values do hold when the distribution is sufficiently nice. And I'm going to give an example of that in a couple slides.
With the definition of gamma, with respect to the actual distribution and not like samples, right?
Yeah. So that's kind of, I'll say in maybe 2 slides, but that's kind of why we see the square root of D over N, is because we're sampling from the distribution. And so we end up getting this term here, just based on like classic results from learning theory.
I guess I mean like the distributions have this parameter D. Like it's a measure of like how nice they are.
Or it's how nice the utility functions are, kind of if you think about VC dimension or pseudo dimension.
D is a function of the iterative value function?
Of the utility functions, which may be a product of like the allocation and the payment function of the auction.
Is it fair to say that D kind of depends on everything that goes into the auction, including this payment allocation function, whereas like this W and K only depends on the utility?
Yeah.
The utility still depend on everything else as well?
Yeah. Okay. Yeah, they're both kind of characterizing the complexity of these function classes. Okay, so here's just the proof idea. So let's say that you take a value and a reported value, which are just somewhere in your evaluation space, and then you snap them to the W grid. Then you could imagine that average utility, or you should believe me that average utility is only going to change by LW plus 2K over N. Just by the utility functions are only going to change by that much. Where L is the Lipschitz parameter, W and K they're dispersion parameters, and N is the number of samples. So that's kind of why we see this LW plus K over N term there. And then second, we're only sampling from the distribution. We don't actually get to know the distribution. So we get another square root of D over N in our bound, which is error incurred from sampling.
Just one more question. If you could solve the maximization problem exactly, that you would just have the root D over N.
Yeah. Yep. Yeah, that's a good question. Yeah.
And do you know like conditions on the distributions that make D small?
So D is worst case over distributions. So it's just going to be small based on kind of the complexity of these utility functions. But we could replace it with a distribution dependent measure that might be better, depending on how nice the distribution is, like Rademacher complexity. Okay, so I just want to give one application, which is the first price auction. Okay, so here's what I mean by when is a distribution nice. Let's say that this interval 0 kappa contains the range of the density functions defining the distribution over the buyer's values. So basically what this is saying is that there's no like point masses in this distribution. They're all like somehow, it's kind of like a nice distribution depending on kappa. So with high probability, the difference between our estimate gamma hat and the true IC approximation factor gamma is the number of bidders plus 1 over kappa divided by square root of the number of samples. And so to prove this, we have to prove basically that the samples induce this WK L Lipschitz condition. I'm not going to prove all of that, but I'll just prove one helpful lemma. which is that with probability 1 minus delta over the draw of the samples, for any bidder I and every value vi they might have, if you look at utility as a function of the bid, vi tilde, so that's what this function is for that first sample, look at this function for all n many samples, these functions are wk dispersed, and specifically with the values 1 over kappa square root of n, and k is basically square root of n. So these were the nice parameters of w and k that we saw earlier, in which makes our bound go to 0. And I'm just going to give a proof sketch of this fact. So I've just rewritten it above. With high probability, for any true value, these functions are wk dispersed. OK, and I want to point out one little subtlety, which is that we're proving with high probability, for any value vi, these functions are dispersed. We're not proving that for any vi with high probability, the functions are dispersed. So in other words, we're proving with high probability, infinitely many function sequences are dispersed because there's one function sequence per value vi. So that kind of makes it more interesting. Okay, so here's the proof sketch. Let's remember what this utility function looked like. Right? As we vary the bid vi, if this bid vi is smaller than the max competing value, the utility is 0. And once the bid is greater than the max competing value, it's just the value minus the bid. Okay, and in other words, like if we're looking at the utility function corresponding to the jth sample, this discontinuity happens at the L infinity norm of that sample. So in other words, for any true value vi, the discontinuity of this function, measuring utility as a function of the bid, happens at this L infinity norm of the sample vi to the j. So that means there's a lot of structure among these infinitely many function sequences. In other words, no matter what vi is, like in any of these infinitely many function sequences, the discontinuity happens at the same place. So there's a lot of structure we can use. In other words, we just need to show that these n many L infinity norms aren't too concentrated. And that will imply that no matter what vi is, those functions are dispersed. And to show that these L infinity norms aren't too concentrated, we just use that like the components have density functions whose range is bounded between 0 and kappa, which kind of controls how well these points concentrate. Okay, so that's kind of an idea of how we prove that so long as these density functions have bounded range, with high probability, our estimate goes to 0 as the number of samples grows. Or our estimation error goes to 0. And I just want to mention that, so that was the case when the bidders have a one-dimensional value. And what about multidimensional values? This is true in a few of the auction classes I talked about: discriminatory auction, uniform price auction, generalized second price auction. And we do analyze these, and these are kind of more interesting because now we have to think about these utility functions over a multidimensional space. And it turns out the discontinuities are now hyperplanes. And we just have to prove that basically any W ball is not going to intersect with too many of these hyperplanes. So it gets more interesting in higher dimensions. So to conclude, we provide techniques for estimating how far a mechanism is from incentive compatible. We introduce an empirical variant of incentive compatibility, approximate incentive compatibility, and we bound our estimates error using this notion of dispersion. We provide guarantees for a bunch of different auction classes. We saw the first price auction, but we also do combinatorial first price auction. We also do generalized second price auction, discriminatory auction, uniform price auction, and an auction I didn't even talk about, which is called the second price auction under spiteful agents. Okay, so here are just a few future directions. So what if the samples can be strategically manipulated? We assumed that we got samples from the true distribution over the buyer's true values. But what if this isn't actually the case? What if they're somehow manipulated strategically, maybe corresponding to some like Bayes-Nash equilibrium of the auctions we're looking at? And this question, what if the samples are strategically manipulated, also applies to the literature on revenue maximization via machine learning. I'm also interested in other applications of dispersion. So in our original 2018 paper on dispersion, we looked at it in the context of online learning and differential privacy. So I think it's a very general notion that can be used in a lot of different ways. And then finally, what about the case when the type space is not real valued? So for example, what about school choice mechanisms where the students are reporting preference orderings over schools? Oftentimes these kind of social choice mechanisms are not incentive compatible, and can we say something about estimating how far they are from incentive compatible? So thank you.
So I didn't understand. But at a high level then, the soundbite is that the bond auctions are approximate incentive auctions under reasonable assumptions?
The which auctions?
The ones you mentioned, bond.
Oh yeah, I guess.
The high level bid is, since there's enough players, they're already automatically incentive, given a bunch of assumptions?
Yeah, I guess.
The sound level, high level of.
Yeah, or at least, so as long as that gamma is small, the incentive compatibility approximation factor. So you're saying the agent, if they reported their value wrongly, they would only gain a teeny tiny bit. Maybe they're not even incentivized. They don't care enough to actually report strategically.
So let's put it, I mean, does the government then optimize its position with this auction? Let's not worry about the bidding. I mean, in some sense, the government cares is that they maximize their.
Yeah.
Right?
Yeah.
Somehow in the end, that seems to be the goal, but it gets lost at some point.
Yeah, so it's just tricky because I don't want to say anything about specifically like you can use this to optimize some kind of trade-off between incentive compatibility and revenue. Because if it turns out that gamma is large, then the agents might do something totally crazy, and you're not going to assume that they're reporting truthfully. So I guess it's just the goal is just to be able to estimate these kind of fundamental properties of these mechanisms without necessarily committing to some like further plan of action that we can use this for. If that makes sense. Okay. Mm-hmm.
So are there auctions that are used that are incentive compatible in some domain of people's utilities, but not in others, where a mechanism like this could say, where an estimation like this could say, oh well, while in principle this might not be incentive compatible, the way you're using it is actually fine, or are those pretty rare?
Oh yeah, I guess one thing is like maybe on a worst case distribution, exactly. The gamma, the incentive compatibility approximation factor is big, but then you find on your specific distribution it's small. And yeah, so then you might be more comfortable with just assuming the agents are going to behave truthfully. Yeah. Okay, thank you.